Hello and welcome to INA's CCI Service Provider version 5 learning path. My name is Rohit Pardasani and I would be your instructor throughout this learning path. For some of you who do not know me, I have about 5 CCIs: CCI and route switch, security, voice, collaboration, and service provider. Today in this class, we would basically be talking about OSPF version 3 network types. So how different is OSPF version 3 from OSPF version 2? It's pretty much the same, with the network types being pretty much the same. If you remember, in OSPF version 2, we had point-to-point, we had point-to-multipoint, we had non-broadcast, we had the broadcast segment, and then we had a point-to-multipoint non-broadcast. As far as OSPF version 3 is concerned, OSPF version 3 has again point-to-point, we have point-to-multipoint, we have non-broadcast, we have broadcast, and we have point-to-multipoint non-broadcast, which is basically a combination of point-to-multipoint and non-broadcast. And there's one more which we can think of, which is MANET, which is mobile ad hoc networks. So let's look at these network types one by one and look at the differences, how they are different from OSPF version 2. So the first network type that we would talk about is going to be point-to-point. Same like OSPF version 2, it's the most simplest form of network type. It's mainly the default network type when you have WAN links, or if you are using tunnels for DMVPN, then by default the network type is point-to-point. As far as point-to-point is concerned, as the name says, it is basically a connection between two routers. There cannot be more than two routers. It's just two routers. So it's just you and me who can establish a neighborship. So if I run OSPF and I connect a link between you and me can establish an OSPF adjacency. It does not really matter if it is a WAN link or it's a broadcast segment. Even if I connect two routers using an Ethernet segment, I could still have my network type as point-to-point. The key point here is that in point-to-point, there are only two routers. Now, if you remember, for OSPF adjacency to form, your hello and dead should be the same. As far as point-to-point is concerned, the hello timer is 10 seconds, and for the dead interval is basically 40 seconds. So as long as your network type is the same between two routers, and your hello and dead is kept the same, which is default 10 and 40, you should be able to establish an OSPF adjacency. In point-to-point, there is no need for a DR election, and neighborship is automatic. So if I activate OSPF on the link, you will start sending multicast packets on that link, and the OSPF source of the packet is going to be a unicast, destination is going to be a multicast, which is 224.0.0.5. So I do not need to activate the neighborship manually by giving a neighbor statement. Neighborship happens automatically as long as you activate OSPF on the interface or under the process. And again, there is no DR or BDR election because there are only two people on that link, just you and me. That is basically point-to-point. If you look at this diagram here, we have two routers. They are connected through a WAN link or even an Ethernet segment, doesn't really matter. I could still change the network type to point-to-point. Here, router 1 is going to send a unicast as a source, and destination would be a multicast to router 2, and the destination address would be 224.0.0.5. You could always verify that with a debug IPv6 OSPF adjacency, or even with debug IPv6 OSPF hellos. The next network type that we have is a broadcast segment. An Ethernet segment is an example of a broadcast segment. So here I could have two routers in that broadcast segment, or I could have more than two. That's why it's called as a broadcast segment. Here, in a broadcast segment, a DR would definitely be elected. There has to be a DR, which is designated router. There has to be one designated router, and that gets elected automatically in a broadcast segment. The whole reason for a DR to be elected is to reduce the amount of LSAs, the floods which would be there in that broadcast domain. Because imagine if I have, let's say, 5 routers in a broadcast segment, what's going to happen without a DR? Assumingly there was no DR concept. what would happen? Router 1 would send an update to maybe router 2, and router 2 would send the same information to router 3. Router 3 would send the same information back to router 2 and to 4, and 4 would send that information to everybody else again. What's the problem in this design without a DR? The same information is being propagated again and again throughout your broadcast segment, which is non-desirable. That's why a DR gets elected in a broadcast segment where every router would send the update to the DR. It is the DR's job to send the update back to everyone else. So router 1, who's not a DR, would be called as DR other, would basically send the update to a DR, which is designated router, and the designated router sends the update to router 3, maybe, who's another DR other. Now, how does the DR get elected? Well, that happens automatically. There is an election process that happens similar to OSPF version 2. That election process starts as soon as I activate OSPF process. And the election is based on the priority. Again, the priority is the same like OSPF version 2. So if you compare version 2 with version 3, they're pretty much the same with just the command difference where instead of me activating OSPF with IP OSPF process ID area 0, I would say IPv6 OSPF process ID area 0. So as far as the election is concerned, again, it's based on the priority. The default priority is 1. Higher is better. So if I change the priority to a higher value, that router would be elected as the DR. And the second highest router would be elected as the backup DR, which is the backup designated router. Every DR other router would only form adjacency with the DR and the BDR. A DR other and another DR other would not form full adjacency. They would be stuck at two-way state, which basically means that they know each other, they know each other's router ID. Again, what happens if the priority is the same? In that case, the deciding factor would be the router ID. Whichever router has the highest router ID wins, and that gets elected as the DR. Now here, the hello and dead is pretty much similar to point-to-point. If you remember, point-to-point was 10 and 40. Even in a broadcast segment, your hello interval and your dead interval is 10 and 40. As long as your hello and dead is the same, and as long as you have a DR in a broadcast segment, your neighborship should form and you should receive all your routes. Do you think I need to give a manual neighborship, or do I need to establish a manual neighborship? No, because in a broadcast segment, your neighborship happens automatically. Again, that's a multicast. The source would be a unicast, destination would be a multicast. Again, on the same address, 224.0.0.5. So here, if you look at this diagram, I have router 1, 2, 3, and 4, where let's assume that router 1 becomes the DR, and router 2, router 3, and router 4, they all are DR others. Remember, a BDR is not mandatory, but a DR in a broadcast segment is mandatory. So if router 1 is the DR, if he has to give updates, he will give updates to everyone. Router 2, if he has to give an update, he would not give it to router 3, he would only give it to router 1. It is the DR's job to send the updates to everyone. The next network type is non-broadcast. So unfortunately, not all multi-access technologies support broadcast. For example, frame relay or ATM. They don't support broadcast. So in that case, how do I establish my OSPF version 3 neighborship? Well, that can be done with manual neighborship. So in non-broadcast, we basically don't support broadcast or a multicast on that segment. That basically means that when two routers want to communicate with each other, we need to send unicast to each other. So there's no multicast in a non-broadcast segment. So if router 1 wants to establish a neighborship with router 2, router 1 would send the source as a unicast, destination would also be a unicast. And for us to establish the OSPF version 3 neighborship, we must give neighbor command on any one of the router, and that neighbor should be your link local address. So we'll in fact see this when we actually configure this and verify if the address is going to be a link local or an actual global address. As far as the hello and dead is concerned, the hello and dead is different from point to point and different from broadcast. Point to point and broadcast was 10 and 40. Non-broadcast is 30 and 120. Is there a DR being elected in a non-broadcast segment? Think about it. It's non-broadcast, right? It doesn't support broadcast. However, there can be more than two people. Anytime you have more than two people in a segment, there should be a DR being elected. So here, there is a DR election happening, and that DR election happens automatically. But you must keep one thing in mind, that if you have a hub and spoke environment, something like a frame relay, which probably you would not see nowadays, but if you did have a hub and spoke environment, or even if, let's say, if you had DMVPN for IPv6, you should ensure that your hub is the DR. You must go to all your spokes and set the priority to 0, because you don't want your spokes to be elected as the DR, because your branch offices would only talk to the hub side. That's why the hub should be the DR. As far as neighborship is concerned, neighborship is manual. It does not happen automatically. You have to give the neighbor statement. So again here, this is an example of, could be maybe a frame relay or even an ATM, where router 1 connects to multiple branch offices, but because my connectivity type does not support broadcast, I would move to the network type as non-broadcast. Then we have the point-to-multipoint network type. So in point-to-multipoint, it basically approaches the non-broadcast limitation, where we could not have broadcast, we had to do manual neighborship. So it basically approaches that limitation in a different manner. So rather than trying to emulate a broadcast capability, it basically tries to form point-to-point with multiple routers in the same subnet. So it's something like, it's still like one broadcast domain, one subnet. Everybody is in the same subnet. They all have the same subnet IP address range, but it still emulates to be something like a point-to-point. So the hub would form a point-to-point neighborship with a branch office, and the hub would also form a point-to-point with another branch office. But if let's say a branch office 1 wants to communicate with branch office 2, it has to go through hub. That's why it's called as point-to-multipoint. Here, the hello and dead is similar to non-broadcast. It's 30 and 120. Is there a DR election in point-to-multipoint? No. Do I require manual neighborship in point-to-multipoint? No. Neighborship is automatic because point-to-multipoint supports broadcast, which means it supports multicast. So my neighborship is going to be, source would be a unicast, destination would be a multicast on 224.0.0.5. And again, there is no DR being elected in point-to-multipoint. Then we finally have the next network type, which is a combination of point-to-multipoint and non-broadcast. This is basically similar to point-to-multipoint and also similar to non-broadcast. So basically, like point-to-multipoint, there is no need for me to give a manual neighbor. Neighborship happens automatically. And like non-broadcast, there is a DR election. The next network type is point-to-multipoint non-broadcast. Like the name says, it is a combination of point-to-multipoint and non-broadcast. So the difference is that like point-to-multipoint, I basically do not have a DR election. If you remember, in point-to-multipoint, there was no DR election. And like non-broadcast, there's manual neighborship. That's why it's called as point-to-multipoint non-broadcast. It's a combination of both. So I basically don't support broadcast. I need manual neighborship, but there is no DR election. That's why it is point-to-multipoint. The hello and dead is pretty similar to point-to-multipoint or non-broadcast. It is 30 and 120. Again, manual neighborship required. The last network type that we have is MANET, which is mobile ad hoc networks. If you look at traditional networks, everybody thinks about routers or machines being connected to a network through a wired technology. However, what happens about mobile devices who basically need to connect to your infrastructure? So basically, users now expect mobile devices to seamlessly coexist with your wired infrastructure. And so think about MANET as a mobile ad hoc network without a central base station. There is no central base station. So because there's no central base station in a MANET environment, everybody needs to form adjacency with everyone. An example for MANET protocol which you can use to support MANET would be OSPF. So OSPF is a good routing protocol which is basically a good candidate for connecting mobile ad hoc networks. So let's do one thing now. Let's connect to our routers and actually see all of these network types. We'll actually establish OSPFv3 adjacency between routers, and we'll change the network types to verify hello and dead, to verify if the neighborship happens automatically, and also to verify if the source is a unicast and destination is a unicast or a multicast. So we would take two routers. One would be an iOS XZ and one would be an iOS XR. All right, so now I have two routers here. I have R6 and I have iOS XR1. They have already been pre-configured for OSPF adjacency. Let me in fact show you that. Show run section IPv6 router OSPF. So R6 has been configured for OSPF, IPv6 OSPF, and XR1 has also been pre-configured for OSPF, which should be under router, show run router OSPFv3, and you should see my OSPF basically being pre-configured. I can verify my OSPF adjacency with show OSPFv3 neighbor. I have router 6 as my neighbor, and show route OSPF should show me routes coming from R6. So let's do a show route IPv6 OSPF, and I have router 6's loopback. So let's look at the network type. I really haven't configured any network type on my interface. If you actually go and re-verify my interface, I really haven't done anything because my connectivity type is broadcast. It's an Ethernet segment that connects XR1 and R6. So by default, it's going to be network type as broadcast. So if I go back to router 6 and let's do a show interface or show IPv6 OSPF interface gig 1.619, you would see that my default network type is broadcast. OSPF automatically detects that because I'm connecting the two routers using Ethernet segment. It automatically detects that your network type is broadcast. Your hello and dead is 10 and 40, and there was a DR which was being elected, which you can see here, that router, in fact XR1 19191919, which is the router ID of XR1. XR1 has become the DR because the priority must have been same. Since the priority is same, it goes to the router ID. So if you do a show IPv6 OSPF neighbor, you would see the neighbor's priority, which is by default 1, and my state is full, and a DR is being elected. The DR is right now XR1. So if I do want to change that, I can change that. I could change that on any router. Maybe if I want R6 to be the DR, I could go to R6 and change my priority so that R6 gets elected as the DR. For doing that, you can go to your interface gig 1.619 and give the command IPv6 OSPF 1 priority, or in fact IPv6 OSPF priority, and define the priority value. You do not need to give the process ID if you're setting the priority. So IPv6 OSPF priority, and let's set this to a higher value, maybe 150. And now you would see that R6 gets elected as the DR. So if I go and verify, you would not see it at this point of time, because whenever a DR is elected, there is no preemption by default. So only if a DR goes down, only then the remote router becomes the DR. But even though I have R6 configured with a higher priority, it's not going to be the DR till XR1 goes down. So going back to R6, let's do a clear IPv6 OSPF process and say yes. Now what's going to happen is that R6 has gone down, and let's also bring XR1 down. So R6 should be elected as the DR. Again, let's do a clear OSPFv3 process and say yes. You would see that R6 should be elected as a DR because XR1, who was the original DR, went down, and this time a re-election happens and R6 has a higher priority and he wins and R6 becomes the DR. Let's verify that. Show IPv6 OSPF neighbor. I can see right now that XR1 is no more the DR. He's in fact the BDR, backup designated router. He's no more the DR. If I want that XR1 should never be the DR at all, then I can go back to XR1 and set his priority to 0. So that's going to be under router OSPFv3 1 area 0. Go under your interface gig 0000.619, and here I would set my priority to 0. Let's do a commit. So once I do that, if I go back to R6 and again verify my OSPF neighbor, you should see that the priority has changed to now 0, which means that even if R6 goes down and comes back up, he would always be elected as the DR. As far as XR1 is concerned, if I do a show OSPFv3 neighbor, you would see that router 6 has a priority of 1. Again, to verify your hello and dead, you can always do a show IPv6 OSPF interface gig 1.619, and that would show me my hello and dead and who the DR is and what's my network type. So this was the broadcast segment. This happened automatically. I did not set any network type on my interface. OSPF automatically detected that the network type should be broadcast because my connection was a gig port, which is an Ethernet segment between the two routers. What I'm going to do next is I would change my network type to now be point-to-point, where in point-to-point you would see that my hello and dead is 10 and 40, and because in point-to-point there is no DR election, so you would not see any DR or even a BDR. So let's go back and change that. I will go back to my XR1 under my OSPF process, under area 0, interface gig 0000.619, and here I would change my network type to point-to multi-point, or in fact point-to-point as per our requirement, so point-to-point. So the minute I do this, I should have some problem in my adjacency because point-to-point does not have a DR segment, and R6 has still not been configured. R6 is still running broadcast, so he has a DR, which himself is the DR, and the other side says there should not be any DR in a point-to-point, so I would have problems in my adjacency. Let's do a commit. And if you see, my OSPF neighborship went down because it says that network type mismatch, you are probably using a broadcast segment and there's a DR on your side, and on my side, I'm not expecting a DR. So I have to go and change my network type on R6 also, because if you remember, for OSPF adjacency to farm, you should have your hello and dead same. They should be in the same area. Your MTU should match. Your stub flag should match. Your network type should also match. So I'm going to go back to R6 under my interface gig 1.619 and say IPv6 OSPF network type. So network should be here, network. So network should be point to point. The minute I do this, my neighborship between 6 and XR1 should come back up. And as you can see, it was just, it just says that loading to full, which basically means that my neighborship is back up. To verify my neighborship, we can always do a show IPv6 OSPF interface. So let's do a show IPv6 OSPF neighbor first. That shows me my neighborship is up. If you notice here that it says that the state is full, but right next to that, I just see nothing there. I just see a dash, which basically means that there was no DR election in point-to-point. Otherwise, you would see here as a DR or a BDR or DR other. Because in point-to-point there's no DR election, it shows you that there is nothing there, there's no DR election. You can also verify that with show IPv6 OSPF interface gig 1.619. You can see that my network type is point-to-point, my hello and dead is 10 and 40, and I don't see a DR anywhere in this output. If you remember the previous output, it showed me DR and the BDR, but point-to-point does not. So this is network type point-to-point. The next one that we would move on to would be non-broadcast. If you remember, in non-broadcast, we had to do manual neighborship. There was a DR election, which was automatic. You should always have the hub as the DR, but the neighborship was not automatic. Now, if you see in point-to-point or non-broadcast, or in fact in point-to-point and broadcast, I never gave neighbor command. I just activated OSPF, my neighborship came back up because my source was a unicast and my destination was a multicast. Let me in fact show you that before I change to non-broadcast. So if I do a debug IPv6 OSPF hellos, you should see that R6 is sending a hello packet to XR1, and the source is a unicast. But look at the destination. The destination is basically this address, which is the link local address, which you can see here. I received a link local address, which is the link local address of XR1. So it's something similar to how in IPv4, my source is a unicast, my destination is a multicast. Here, I'm going to send the request from the source being an IPv6 unicast address and destination being an IPv6 multicast address. Let's do an unall. Again, you can look here that this is my something similar to IPv4, where in IPv4 it was 224.0.0.5. However, in IPv6, it is FF02::5, which is equivalent to 224.0.0.5 in IPv4. So source is a unicast address. Destination is an IPv6 multicast address for OSPF, which is FF02::5. So let's go now and change my network type to in fact non-broadcast. So for that, I would go back to my interface gig 619 and say IPv6 OSPF network type non-broadcast. And on XR1, I would do the same thing. So I have route OSPF1 area 0 interface gig 0000.619, and here I would give my network type as non-broadcast. Notice that my OSPF adjacency would not come up between the two routers. So even if I wait for 1 minute, my neighborship would not form between R6 and XR1. Because what's happening, my network type is non-broadcast, which means that does not allow OSPF to send the request as a unicast as source and destination as FF02::5, which is the multicast address for OSPF for IPv6. It does not allow that because my segment does not support broadcast, which means it doesn't support multicast. So what do I need? I need a manual neighborship. That's what we would give now. I would give a manual neighborship on any one of the router. So if I send you a unicast, you would respond back as a unicast. I don't need to give neighbor statement on both the routers, on any one router. Typically, you would give that neighbor statement on the hub. So let's go to XR1. Let's just first, in fact, verify if my neighborship is back up. I would go and do a show OSPFv3 neighbor. As you can see, I do not have any neighbors. The only reason being is that it does not support multicast. So let's go back to XR1, and on any one router, maybe on XR1, I would go and say router OSPFv3 1, area 0. So that should be router OSPFv3, and then area 0, interface gig 0000.619, and here I would give neighbor. Now what should I give as the neighbor's address? Let's go and give the physical IP of the neighbor. Let's do a show IPv6 interface brief. So this is the physical IP of R6, right? Let's go to XR1 and say neighbor R6. And let's do a commit. Once I give commit, I basically get an error which basically says that, okay, something was wrong, there's some problem, and we can verify that problem with the show configuration failed. Let's do that. It shows me that the command that I entered was wrong because the neighbor should be a link local address. If you remember earlier, I told you that when you give the neighbor statement, your neighbor should not be the actual physical IPv6 address. It should not be the global address. It should be the link local address of the neighbor. So because all my control plane communication happens through the link local address, so my source is a unicast, which is going to be my link local address, and destination is the multicast. But because we're using non-broadcast, my source would be a unicast, destination should also be a unicast, and that destination should be a link local address. So let's go and now give the link local address neighbor and take R6's link local address, which is FE80, so this one, and go to XR1 and let's retype that and do a commit. Obviously, I would have to go and remove that command, the previous command that I gave. Let me exit out completely and say no. So I'm not saving that config. Let's go back to router OSPFv3 1, area 0, interface gig 0000.619, and re-give that command with the link local address this time and do a commit. Once I do a commit, my OSPF adjacency between R6 and XR1 should come up. Let's verify that with show OSPF v3 neighbor. I have my neighbor coming up. It's still not up yet. It's still in the attempt state, but it should come up in a few minutes. Let's verify on R6 also. Show OSPF, show IPv6, OSPF, neighbor. So neighborship hasn't really formed yet. Now, if you remember that there is a DR election that happens in non-broadcast, right? From the earlier configuration, we had set the priority of XR1 as 0. That's probably causing the problem because I've given the neighbor statement on XR1 and his priority is 0. So I'm going to go back and change his priority to maybe be 1, and then we'll see if the neighborship comes back up. So let's go back to XR1 and set his priority to be maybe 1. To interface gig 0000.619 and change my priority to 1 and do a commit. Let's verify show OSPFv3 neighbor. My neighborship is back now up and running, and R6 has been elected as the DR. because R6 has a higher priority. Even though R6 has a lower router ID than XR1, R6 still gets elected because priority is the first deciding factor between the two routers. Only if the priority is same, only then the router ID would be elected as the DR, as the deciding factor. But because R6 has the priority set as 150, R6 becomes the DR. So you see, in non-broadcast, my neighborship does not happen automatically. I have to give the neighbor statement. And neighbor statement does not need to be given on both the routers. On any one router, you can give the neighbor statement. And DR gets elected automatically. And if you look at my debug now, this time I should see that the source was a unicast and destination was also a unicast. Let's go back and do a debug IPv6 OSPF hellos and look at what request or what hello packet came from XR1. You should see that the destination would not be FF02::5. Instead, it would be the unicast address that I had given. So I have here, which you can see, sending hellos from source unicast, destination is also unicast. It's no more the multicast address in IPv6, which normally happens in broadcast segment or even in point-to-point, because non-broadcast does not really support multicast. So you have to give the neighbor statement to make it unicast. Only then your neighborship would form. So now let's go ahead and change our network type to be point-to-multipoint. If you remember, in point-to-multipoint, there is no DR election and neighborship happens automatically. If you remember, point-to-multipoint was a collection of point-to-points together. So I'm going to go back to 6 and change my network type. So interface gig 1.619 and say IPv6 OSPF network type as point-to-multipoint. And let's go to XR1 also. Before I change it on XR1, obviously my neighborship is going to be affected because of different network types. But before I change on XR1, I just quickly want to show you the hello and dead for non-broadcast before I change it. So show OSPFv3 interface gig 0000.619. You would see that I'm running non-broadcast. I have a DR election, and hello and dead is 30 and 120. So now let's go to XR1 also and change my network type to point-to-multipoint. So config T, router, OSPFv3 1, area 0, interface gig 0000.619. And here I would change my network to be point-to-multipoint. The minute I give this, I don't need the neighbor statement. I could go and remove my neighbor statement from earlier, which I had done, because I don't need the neighbor anymore. Because in point-to-multipoint, neighborship is automatic because point-to-multipoint supports broadcast. It supports multicast also. So I don't need the neighbor statement. There is no DR, there is no neighbor statement required. Let's do a no and do a commit. Let's verify our OSPF adjacency. Show OSPFv3 neighbor. As you can see, my neighborship is up. There is no DR being elected, and I did not give the neighbor statement. Here, if I look at my debug, the source would be a unicast and destination would be the multicast address, which is equivalent to 224.0.0.5, which is actually FF02::5. Let's verify that. So going back to 6, I have my debugs turned on, and now you can see I'm sending the hello to a multicast address sourced from the unicast, which is my link local address of R6. Lastly, let's change our network type to a combination of point-to-multipoint non-broadcast. So before doing that, I'm going to quickly show you my interface of R6 just to show you the hello and dead for point-to-multipoint. So show IPv6 OSPF interface gig 1.619. As you can see, there is no DR being elected. My hello and dead is 30 and 120, and my network type is point to multipoint. Remember, point to multipoint is a collection of point-to-points together. So now, finally, what we would see is I would change my network type to be a combination of both point to multipoint and non-broadcast. This time, like point to multipoint, no DR would be elected, and like non-broadcast, I will have to give manual neighborship. Let's verify that. So on R6, I would go back to my interface gig 1.619 and say IPv6 OSPF network point to multipoint non-broadcast, which is a combination of both. And let's go to XR1 and change it here also. So router OSPFv3 1 area 0 interface gig 0000.619 and network point to multipoint non-broadcast. Let's do a commit. Will I establish neighborship automatically now? No, because in non-broadcast we had to give manual neighborship, so my neighborship would not form. Will I have a DR being elected? No, because in multipoint there's no DR. Let's verify that. So if I do a show OSPF v3 neighbor, I do not have neighborship at this point of time because I haven't given the neighbor statement. Let's go and give the neighbor statement. So config t router OSPF v3 1 area 0 interface gig 0000.619 and neighbor should be R6's link local address. Let's scroll back up and check his link local address, which I believe was here. Or in fact, I'll just give the command. Show IPv6 interface brief. That's the link local address of R6. Go back to XR1 and say neighbor, the link local address of R6. Commit. My neighborship should now establish between R6 and XR1. Let's verify that. Show OSPF v3 neighbor. My neighborship is up and running. As you can see, there is no DR being elected like point to multipoint. And like non-broadcast, I gave the neighbor statement, which means if I look at my debug, I would see source as unicast and destination would be also a unicast because of the neighbor statement, and there would be a DR. So looking back at R6, you would see here that he is sending a hello packet from the source as unicast and destination as unicast. So that basically proves that we are using unicast, not multicast. And if I do a show IPv6 OSPF interface gig 1.619, you would see that my network type is point to multipoint, non-broadcast. In fact, here it's showing me as point to multipoint. Let's go and verify my interface gig 1.619. I have given point to multipoint non-broadcast, but in my show command, it's still going to show me as point to multipoint. It's not going to show you as point to multipoint non-broadcast. However, I still require a neighbor statement. And if you notice that a DR would have been elected, or in fact a DR would not be elected, which you can see here, there is no DR being elected in my show command. I hope this video was informative to you, and thank you for viewing.